so here are my solutions to the first problem. Actually, I'm only going to do the first two problems in this video. So in the first problem, we start as usual by looking at the goal, which you recall is f of x minus L. In this case, f of x is just the constant function 1, and L is the number 1, so that trivially, no matter what x and d are, this just always computes to 0. E is, by definition, some positive real number. And so it doesn't matter what we choose for D, any choice will work. And so we could choose it to be 1 or 10 or anything else. We always get this inequation, and therefore the limit statement holds. Now, let's scrutinize part B. And in part B, the goal is to look at f of x, which is equal to x, L is equal to 2, and find out how can we state this in terms of the quantity related to D, but that in this problem is just the same thing, absolute x minus 2. So we just pick D is equal to E, and the relationship holds. In part C, we are looking at f of x, which is this, minus L, which is 7, and the difference there is -6. We can factor out 2, divide it to the other side, and in fact this tells us exactly what the choice of D should be, or delta should be, epsilon over 2. In the next problem, I realized about halfway through that I actually was doing the limit as x approaches 1, so I need to correct some of these numbers, but in any case, we again start by scrutinizing the goal, which is x cubed minus 8, right? F of x is x cubed, L is 8. And we can factor that using the factorization of a difference of cubes. We divide to the other side, and as we did in the case of x squared, we will constrain D so that we can get bounds on these various expressions. So I'll go ahead and again choose D is equal to a half. Now I don't have to pick that. In fact, in this case, I think I could even pick D to be equal to 1, I think would be acceptable. What happens if I pick D to be equal to 1? Now, this would imply that x is somewhere between 7 and 9. And in that case, x squared would have to be somewhere between x would have to be somewhere between 49 and 81. And then we could evaluate this expression piece by piece, every number being positive. Then the least it could be, because we can minimize this by minimizing each part, really, right? Because everything here is positive and summed together. So really finding the minimum is just finding the minimum of each part. So the minimum would be 49 plus 7 plus 1, which is 57. And the maximum is 81 plus 9 plus 1, which is equal to 91. And so we would like to have a value that is necessarily less than this. That's the inequation that we want. So if I just choose a denominator value less or greater, the maximum of that, which apparently is 91, then it will get the job done. Well, here, let's just ignore that. And so we will pick 91 as the denominator, and therefore D is E over 91. And if you plug everything into the inequation, you should get everything working out as it is supposed to. So that's the proof. Now, on to the next one, we find the limit as x approaches 1 of 1 over x, and we believe that the limiting value is 1. So this is the goal, and we can add fractions, get 1 over x minus x over x, add the fractions, and distribute the absolute value, you get this. Multiply absolute x to the other side, and now we want something less than this as our choice of delta, because that's, we've got x minus 1 here, which is what is related to delta. So we know that the minimum, if we constrain delta to 1/2 this time, keeping it kind of away from 0 where there are problem spots, so we choose delta less than 1/2, and therefore x is between 0.5 and 1.5, right? X has avoided potentially taking on the value 0 or anything like it. So in that case, we want to minimize this side of the inequation, and we pick 0.5. So d equals 0.5e. That's the choice of d, and if you throw everything into the limiting statement, you'll get it all to work out. So in the next one, we look at the limit as x approaches 4 for square root x, and that means that we guess the limiting value is 2. And we can multiply both sides by the conjugate, so that comes back up, and we get this inequation as an equivalent expression. We want to minimize this, right, get some kind of a choice of d that would put us underneath this quantity. So we restrict d to, say, 1/4, why not? And that puts these bounds on x. That means that square root x is between approximately 3.3 and 3.5, but we could just pick 3 to be on the safe side. That'll definitely minimize this quantity, and so that's the solution to the problem, is picking d equals 3e. And we could pick anything, right? We could have picked d equals e, and that would also have worked. Anyway. So the next problem is to prove that there is no limit for this piecewise defined function, which is 1 to the left of 0 and -1 at and to the right of 0. So basically the intuitive problem with this is that the function has a gap. It's up here at 1 to the left, and it's down here. Oops, that was kind of ugly. Let's make that a little bit better. It is -1 to the right of 0. And so what I'm going to exploit is the fact that if I make my e equal to 0.5, if I assume that the limit exists, then I can put bounds around that limit wherever it is. And I know that it must be within a distance of the function value here. It must be within e up here, and it must be within a distance of e, or epsilon, down here as well. So the limit has to be somewhere up here, and it has to be somewhere down here, as long as I choose epsilon small enough. And if I want to keep these separate, I'll pick epsilon equal to 0.5, right? That's a small enough distance from -1 and a small enough distance from 1 so that these don't overlap, and that means that the limiting value has to be in 2 different places, and that's impossible. So that's the kind of picture that I'm working off of. So if I assume that such a limit exists and pick e to be 0.5, then I know that I can look to the left of 0, right? I can pick an x value to the left of 0, and f of x is then equal to 1, and I get that 1 minus L is less than 0.5. But if I pick a corresponding value to the right, then I get that 1 minus L is within that distance. The first inequation implies this, the second one implies this, and just as we discussed, that means that L is satisfying 2 contradictory constraints, and that's a contradiction, so there cannot be a limit.